Hello, Gen Chem. Hello, Chem 105. This is the lecture for Monday, February 17th, covering, this is going to cover electron configurations, and valence electrons. These are the two topics. I'm going to pick up looking at electron configuration from which we were looking at on Friday, and carbon, which has, to remind ourselves, carbon has 6 protons, so therefore it must have 6 electrons, 6 protons. So it must have 6 electrons. The electron configuration for carbon is we have the 1s orbitals in the 1s, the orbitals in the 2s, and the orbitals in the 2p. We can put electrons into here. We have 6 that we need to put into these electron orbitals, and 2 go into the 1s, 2 go into the 2s, the remaining 2 go into the 2p. And that is the electron configuration for carbon. Oxygen would be similar. This has 8 protons, so therefore it must have 8 electrons. So we can do the similar sort of thing, 1s2, 2s2. These always have 2 electrons. They fill first if there are enough electrons to fill them. And then we have the remaining 4 electrons go into the 2p, 2p4. That is oxygen's electron configuration. Similarly, neon in the same row or period. This has 10 valence electrons. 10 electrons. So 10 protons, 10 electrons. So we have 1s2, 2s2, 2p6. There are 3 orbitals in p. 3 p orbitals. Remember, each can hold up to 2 electrons. So we have a total of 6 possible electrons that can go into the 2p orbitals. There are 3 of them there. Let's continue here, and so the next element after neon would be sodium, 11 protons, so therefore 11 electrons if it's neutral. To write the electron configuration for sodium, we have 1s2, 2s2, 2p6, so that's like neon. And now we need to go into the next subshell, the 3s, and put the 11th electron into the 3s orbital. There's only one orbital in 3s. And as written like this, in all of these above, the carbon, the oxygen, neon, now the sodium, these are all what we call full electron configurations. So if I were to ask you to write the full electron configuration for sodium, neon, oxygen, or carbon, you would do these 1s2, 2s2, 2p6, etc. 2p6, 3s1 for sodium, just 2p6 for neon, 2p4 for oxygen, and then 2p2 for carbon. Now there's a shorthand we can do because we realize that the first part of this electron configuration, the 1s2, 2s2, 2p6, is the same as what we see in neon. So there's a shorthand where we can simply indicate, because that's equal to neon, we can replace this whole first part with neon, and then simply write the remaining 3s1. So neon in brackets like this plus 3s1 is what we call the noble gas shorthand electron configuration. We only do this with the noble gases, so neon, argon, krypton, they can be used to shorten how much you have to write when you're doing electron configurations. Now, electron configurations are important because they help us understand valence electrons. Let me shift here and to talk more about valence electrons. The valence electrons are the electrons. Valence electrons are the electrons in outermost shell. These are called valence electrons. So for outermost shell, that means you look for shell with the highest number. For example, in carbon, the 2s2 and 2p2, these are the highest shell. The 2 is the highest shell. Oxygen and neon, the 2s and 2p are also the highest shells. In sodium, though, we have something different. The highest shell is 3s, because 3 is more than 2. So anything with 3 then would be part of the valence electrons for that element. So it's the electrons in the highest shell number. These are the valence electrons. So carbon here would have 2 valence. I'm going to abbreviate valence electrons like that. Oxygen would have 6. Not 2, it's 4. There are 2 in 2s2 and 2 in 2p2, so there are 4 valence electrons in carbon. There's 6 in oxygen. There are 8 in neon. Sodium has 1 valence electron because there's only 1 electron in the 3s. The periodic table is arranged to help us figure out where these valence electrons are. We have it arranged something like this. It's my crude drawing. Something like this. This over here is called the S block. This is the D block. And the P block elements. And then down below here we've got the 4F. The 4F block, 5F block, that's a 5. And this shows us where valence electrons are being filled. So elements that are found in the P block have valence electrons in the P and also S. Elements that are just in the S only have valence electrons in the S. Elements in the D block have valence electrons in the D block, in the Ds. That's because the d orbitals, d subshells are being filled. The d orbitals in the d subshell is being filled. Now, hydrogen, which is just 1s, and then helium. These are a bit different. 2s, because they only have period 1 or row 1 is a bit different, some exception, because we only have the 1s1 and 1s2 electron configurations. They sort of fit in with both 2s. Helium here fits in with the noble gases over here, and hydrogen fits in with the group 1 elements, but they're also a bit different, so they sort of stick out on their own. All right, now let's move on, and we're going to keep talking about valence electrons. I'm going to clear the page here. I'm erasing the board, and we will start over. Delete. All right, now the valence electrons are important because the group number, actually, so things in, for example, in group 1, they all have one valence electron. Group number let's say elements in a group number have the same number of valence electrons. Elements in a group have same number valence electrons. For example, in group 1 we have hydrogen, lithium, sodium, potassium, hydrogen, lithium, sodium, potassium. They all have just one valence electron. 2s1. If we do their electron configurations, we'll find out that they end up with 1s1, 2s1, 3s1, 4s1, like that. In fact, I could write them as noble gas configurations in this way. Helium, 2s1, and then we have, this would be neon, 3s1, and then argon, 4s1. These are the noble gas shorthand configurations, electron configurations. And the valence electrons are just one each. So again, elements in the same group have the same number of valence electrons. It's important because the number of valence electrons gives chemical properties. The reason why elements in the same group have similar chemical properties is because they have the same number of valence electrons. So another way to say this is the periodic table is organized with same number valence electrons in column or group, which is why they're organized with similar chemical properties in column or group. It turns out that chemical reactivity, that is, chemical reactions, come from adding, subtracting, or sharing valence electrons to fill valence subshells. So it's these valence electrons that cause things to react the way they do, that cause elements to react the way they do, that cause atoms to react the way they do. And we're going to be learning a lot more about that. So, for example, one important thing is that the noble gases, group 18, on the very right, have, if you do their electron configurations, they have completely filled subshells with no room for more valence electrons to be added. It turns out that a completely filled subshell is sort of stable. So completing the noble gas configuration makes it very stable and unreactive. Now, to help us understand how these valence electrons react, we're going to use something called electron dot symbols. And I'm going to start over with a fresh page here. Delete. Electron dot symbols. This is 2.7b in your textbook. And electron dot symbols are very useful for helping us keep track of how valence electrons are available or being used in chemical reactions. So we can start by simply indicating the number of valence electrons on an atom with dots. So hydrogen with its 1s1 valence electron has 1 dot. Carbon with its 2p2 2s2 2p2 valence electrons, or 4 valence electrons, we can indicate with 4 dots. Helium with its 2 valence electrons, 1s2, we can indicate with 2 dots. And by the way, we pair dots if possible. They tend to pair up, like they fill up an orbital. 2 electrons in an orbital, they pair up. Oxygen with its 6 valence electrons, it's 2s2 2p4. We can write it like this: 6 valence electrons. Nitrogen with its 5 valence electrons. And although we want to sort of distribute them around the sides of the atom, it doesn't matter if I put the 2 dots on the top or the bottom. I could do them down here. These are all the same thing. It makes no difference. Or I could put it on the side. They're all the same. So we usually separate them so they're one of the 4 sides. We always separate them so that they're at one of the 4 sides. And then another one would be chlorine. So chlorine has 7 valence electrons, 2s2 2p5. So I can write chlorine like that. It's missing 1 electron to complete its to fill its 2p subshell. Neon has, of course, completely filled its 2p subshell, so it has 2s2 2p6, 8 electrons. 8 electrons around the neon. We can think of these electron dots as sort of like the pieces on a Lego that allow it to fit with other Legos. So these are the pieces that are available to pair up with electrons on other atoms. Neon doesn't have any pieces available. All its electrons are paired up. Chlorine actually has 1 spot to pair up with 1 other atom. Carbon has 4 spots. It can make 4 pairs. Helium doesn't have any spots. It just has the 2. And so these can be very useful for determining chemical reactivity. So the number of valence electrons on element represented by dots. And you can use the electron configuration or the group number to the group number, because you know everything in the same group has the same number of dots. to determine valence electrons or dots. Number of valence electrons or dots. Okay, I'm going to stop at this point, and I look forward to picking this up on Wednesday morning, and we can talk more about how we use electron dot symbols to do chemistry, to make things.